Now that you can evaluate composite functions, we can start composing more general composite functions. So they can be composed in a much more general way without a specific input number, which is not as simple because we're not able to simplify the inside of the composition. The inside function has to stay as a function, and it can get a little bit messy. But the rules are the same. Whatever we see inside the function parentheses, we're going to make that replacement. For example, we can make a new function f of g of x without specifying any input. So the instructions for f of x say that I am going to take the square root of whatever the input is, and I'm going to add 1 to it, and then outside of the square root, I'm going to take away 7. So instead of a number, I have to put this entire function g of x inside the function f. So g of x is x squared minus 3x. So f of g of x is f of x squared minus 3x. So this is where we're going to replace this x with this expression. It's going to go inside here. X squared minus 3x plus 1. Instead of replacing a nice handy number, I have to put this entire x squared minus 3x in there. It doesn't give us an answer, or it doesn't give us a single value, it gives us an expression. So f of g of x, or f of x squared minus 3x is equal to, this can be tidied up a tiny bit, that we don't need the parentheses anymore. X squared minus 3x plus 1, all inside the square root, minus 7. Can also go in the other direction. I can find g of f of x. So the instructions for the function g tell us to take the input, square it, and then subtract 3 of that input. So we will have to do that. Instead of with a number, it's going to be with an entire function. So when I replace x with f of x, the first thing that I do is I square f of x. So that is this squared minus 3 times f of x. So this is not as nice looking. This is f of x all squared minus 3 times f of x. And this can be simplified, but it's pretty messy, and I'm going to leave it for now. To compose this function f with itself, we can treat the inside f of x as the inside and the outside function. So f of this x is now going to get replaced with f of x. This x is going to get replaced with f of x as well. If you like to think about it this way, we can say that this is f of x plus 1 minus 7. And then we can replace f of x with the definition of f of x. So this is going to be the square root of f of x, which is the square root of x plus 1 minus 7, all plus 1 minus 7. So it's a function, this function inside itself, which tends to look pretty strange. There's no sort of rules of how much to simplify this, but because minus 7 plus 1 is pretty easy to do, I'm going to leave it like this. So this is the very general f of x. It looks bad, but this is as good as it gets. We can compose the function g with itself, g of x. So we're replacing this x with g of x. I'm going to write this a little bit differently, because not everyone sees this the same way, and this may be a better way of looking at it. Whatever works, works. G of x says we're going to take g of x and square it, and then we're going to take away 3 times g of x. So if you want to wait before you make this replacement for g of x, this is a perfectly good way of writing it out. And then we can replace g of x with what g of x is, x squared minus 3x, that's still all squared, minus 3 times x squared minus 3x. So again, this can be simplified. I'm not going to do every single step. I'm going to write out the answer for anyone who wants to confirm this for themselves. So we've put the function g of x, replaced each of these x's with g of x, and then tried to simplify the result. We looked at this notation much earlier in the slides, but here it is again. F of g of x could also look like f o g x. So the function that appears furthest to the right is the most inside function, and then as we move to the left, they're the more outside functions. So the inside function here is still g, and the outside function is still f. So if you are asked this O notation, what does f(og) of x mean? It means exactly the same as f of g of x. You write them in the same order, and you replace this x in f with g of x. So this x is going to become g of x. This x is going to become g of x. So that's the sign of g of x. You can write that as a step if you like. Plus 2 times all of g of x squared. You probably won't use this extra step for very long, but it can be really helpful when you're getting started. So g of x we will replace with the definition for g of x, 1 over 1 minus x, plus 2 times g of x is 1 over 1 minus x, all squared. So that's what this notation means. Now that we know how to compose functions, it's also important to know how to decompose functions. So how to write a single function as a composition of 2 or more functions. And there's usually more than one correct way to do it. And perhaps the easiest way of thinking of it is replacing part of the function with a blank. So I'm going to use just a box. And I'm going to say that this looks like something, looks like the far outside idea is that there's something being squared. So that's one of the reasons why it's often called an outside function, is that it sort of appears on the outside of whatever's going on. So I'm going to say that h of x is actually a box squared. So I've got this blank square. So the outside function I'm going to call this f of g of x, and the outside function is a box squared. I'm going to replace that with something much nicer, but that's sort of the way to get started thinking about decomposing functions. The inside function is whatever was inside that box. So the inside function was 4 sine x plus x, and then for the outside function, you're going to replace whatever your box is with x. So instead of box squared, it's going to be x squared. So f of x is x squared, g of x is 4 sine x plus x. When I compose these two functions, when I take g of x and I put it inside f of x, I get this function, h of x, which is equal to 4 sine x plus x all squared. Here's a different function to be decomposed, and there are at least two ways to do this, and I'm going to show you both ways that probably the easiest ways to think about this one. So these are all going to depend on what we're considering to be the outside function and what we are going to replace with a box. So this is 4 to the power of 7x minus 1. So really the main thing that's going on is that 4 is being raised to some power. So if h of x is equal to f of g of x, the main thing that's happening, the outside function, is that we are raising 4 to the power of something. So this is 4 to the power of box. And g of x is whatever was inside that box. So inside that box was 7x minus 1. And now we can go back and replace our box with x. So 4 to the power of x is the outside function, and the inside function is 7x minus 1. But if for some reason I think that the inside function should be 7 times x, then I'm going to decompose this differently. I'm still going to say that it's an outside function and an inside function, but this time my outside function is 4 to the power of box minus 1. Which is a little bit weird, but it's a perfectly valid way of describing this function. G of x is whatever was inside that box, so 7x. And then I can go back and I can replace this box with an x. So this is a different way of defining h of x. The outside function can be 4 to the power of x minus 1, and the inside function can be 7x. And when we put those together in a composition, we will still get the same h of x. And it's almost always possible to do decomposition correctly in more than one way. So I think I've used x for every example so far, but the inputs are not always going to be x, and the functions are not always going to be called f or g. They may have some physical meaning, and you will need to get the inputs and the outputs lined up. So follow the instructions that each function tells you to do, and you will be fine. And I'm going to show you an example of a composition that will only make sense if we do it in one direction. Here's an example of a pair of functions with no x's. They have different letters this time. But I can still compose these two functions, g and s. So if I was asked to find g of s of 5, this is an evaluation, so I can simplify this inside first, find out what s of 5 is, and evaluate that. S of 5, the function s tells us to multiply the input by 60. So 60 times 5 is 300. So s of 5 is 300. Now I can move to the g function and replace the input with 300. So instead of g of s, I have g of 300. So instead of 13s minus 6, I have 13 times 300, all minus 6. And that is equal to 3900 minus 6, or 3894. G of s of 5 is 3984. I can also find the very general function g of s of t. This time we can't simplify anything on the inside, so we're just going to put s of t straight into g. So if I replace this s now with s of t, I will have 13 times s of t minus 6. And s of t is defined as 60 times t. So it will be 13 times 60 times t, which is 780 t minus 6. So in general, g of s of t, if my input is t, my output is 780t minus 6. Here's an application of a composite function. So on each day D, starting on January 1st and until January 15th, B birds show up at a certain feeder where B of D is equal to D squared plus 5. The amount of food in ounces F needed at the feeder depends on the number of birds and is computed as F of B is equal to 2B plus 1. So there's two different functions happening here. The birds are dependent upon the days, and the food is dependent on the birds. So we may need to use a composite function to answer questions depending on what information we have. So we can answer these three questions. How much food is needed for 14 birds? How much food is needed on day 7, on January the 7th? And what does the composite function f of b of d represent? The first question, how much food is needed for 14 birds? We need to choose the correct equation. This one here has food as a function of number of birds. So this says that f of b is equal to 2b plus 1. So food in ounces is f, birds is, number of birds is b. So the number of food we need for 14 birds is f of 14. And f of 14 is 2 times 14 plus 1, or 29. F of 14 is 29, which means that when there are 14 birds, you need 29 ounces of food. The second question was how much food is needed on day 7, on January 7th. So this is a question about food, but it hasn't told us how many birds there are. It's only told us what the day is. So we have to do a bit of work first to find out how many birds there are on January 7th. So this function b of d is equal to d squared plus 5 tells us how many birds depending on what the day is. So b of d is equal to d squared plus 5 is how we will find the number of birds. On day 7, where d is equal to 7, we can plug a 7 in there. We get 7 squared plus 5, which is equal to 54. So that is not the amount of food we need, that's the number of birds. So 54 birds on January the 7th. So now we can put that into the second function. F of b is equal to 2b plus 1 now that we know the number of birds. And f of 54 is equal to 2 times 54 plus 1, which is 109. So f of 54 is 109. So how much food is needed on day 7? 109 ounces of food, because there were 54 birds. The third question was what does the composite function f of b of d represent? So f of b represents the amount of food given the number of birds. B of d represents the number of birds given the date between January 1st and January 15th. So f of b of d represents this part here. The input is days, output is birds. And then the output f of b tells us the amount of food when the input is birds. So f of b of d represents the amount of food needed on a certain day. So we get to skip over the birds altogether. And we can compose this function. Here's f of b, here's b of d. So we're going to replace b with b of d. So we get f of b of d is equal to 2 times b, or b of d, plus 1. And b of d is defined as d squared plus 5. So this is 2 times d squared plus 10 plus 1. So it's 2 times d squared plus 11. And you'll notice that the input b has been taken out of the problem. So we just have this function now, f of, we could also call it f of d. It's f of b of d, but the only input is d. So f of d is equal to 2 times d squared plus 11. So if we were to attempt what we did in the last slide, f of 7 is equal to 2 times 7 squared plus 11. And we get 98 plus 11, or 109 ounces. In summary, it's easiest to evaluate composite functions by evaluating the inside function first and then moving to the outside function, or functions. To compute a general composite function, you will replace the variable of the outside function with an entire function rather than a number, and your answer will be an expression. It will not be, for the most part, it will not be a single value. Composition of functions is not commutative, so it matters which function goes in front unless they're both the same. So f of g of x is not necessarily the same as g of f of x. Functions can be decomposed, and there's often more than one correct decomposition. So if you're doing your homework and you see a different answer in the back of your book, try not to panic. Yours is very likely correct. It's just that everybody can do decompositions differently. And real-world applications of composed functions don't have to be scary. Just try to keep in mind what's the input, what's the output, and what output can become an input.